Our next presentation is from Adithya THONSE from Texas Instruments. Adithya is working as a tinyML expert at TI with 4.5 years of experience in the semiconductor industry, with 2 years of it coming in the deep learning domain in the embedded hardware industry. Currently leading tinyML efforts at TI for a broad range of ARM, Cortex, R, and M-based microcontrollers, predominantly using convolutional neural network-based AI algorithms on sensory and audio time series data, with roles and responsibilities including designing and implementing the architecture of software infrastructure for end-to-end training and compilation of algorithms tailored to specific MCU capabilities. So with that, Adithya, I turn it over to you and take it away.
Thank you, Chris. Yeah, so today I'll be talking about DC arc fault detection, and we are using tinyML for that. So what is that we are talking about here is that, so what is DC arc fault detection? So arcs is something that we would have heard a lot. Arc is basically, I mean, even from the youngest of days when you heard arc, it's basically, when two close wires, wires are really close by and the gap is really small. There's a chance that if they are carrying really high current or high voltage, there's a chance that it sparks in between. Now, when AC, and now again, in terms of current, there's AC current, there's DC current, right? So when you see AC current, we have a lot of these protection devices. We have miniature circuit breakers. We have a lot of devices that are already there to protect these kind of things at our homes, at offices, at everywhere else. But when it comes to DC, there is no zero crossing in terms of voltage. So the voltage doesn't cross a zero line where you can, do a level check and then determine it. So what happens in these kind of things is that in DC, when arcs occur in DC kind of circuits, it's basically it sustains, and that sustenance basically you can imagine, think of the second picture shown over here. When the arc sustains, there's no way to figure out that it's sustaining. I mean, indirectly, it's absolutely like a silent killer. It just exists and then it causes a massive fire. And why is this so much of a concern? Why are we looking so much behind, DC arc faults to be detected? Is because increasingly we're using these DC systems are being used at a very high rate. Say, for example, we have our home inverters, we have photovoltaic. Now that we are moving a lot more towards renewable energy space, there's a lot more of photovoltaic grids, as well as even better, the EV trend, the electric vehicle trend. It's increasing massively, and they have a large battery that is present in the car. Now, you don't want these DC batteries or circuitry to get damaged and unknowingly cause a complete destruction of all these things. These are big problems that we need to be aware about, and predictive maintenance on such things or anomaly detection on this particular aspect is one of the things that, it's really important right now. So how do these wires, get worn out when, after all, when you're buying something new equipment, it is perfect, right? But what happens is that it is now again, like earlier, we've seen that, these wires can be subject to corrosion. It can be subject to wear and tear. It can be subject to environmental degradation. It can even be subject to rodents and stuff like that. And rodents, they don't do a clean job like cutting the wire completely. They can just do a half and, just go away with it. Now that is a big problem for us, right? Like if you have some wires loosely connected, which are carrying really high currents and voltages, you don't want to really mess up your device. You don't want to really, have your power at home go off or power at anywhere go off. So that's where these DC arc faults is such an important thing. Now to detect that, that is where we'll go in. So there's already, because this is such an important topic, there's already a standard which is by UL. It's another standardization organization that mandates that, for all these kind of DC arc faults, let it be series arc fault, let it be parallel arc fault. However, series and parallel is just basically where it occurs in a circuit. That's all. Now, series is in the same wire if it occurs, and parallel is between two wires. So it's not much to worry. It's after all DC arc fault. Now, there's the standard which already mandates how to design a particular arc fault circuit interrupter, or what are the tests that you need to do to say that, this device is a proper interrupter. This device can, properly mitigate or detect these kind of faults. There's already a standard, but however, these existing standards, what have been used till now, are all based on frequency transforms, say Fourier transforms and stuff like that. So what they do every few milliseconds or something, they keep doing an FFT of the time series of the current, and then they project it, and then they have their own FFT metrics and stuff like that to say that is this a fault or not? Is this a fault or not? Basically, is this an arc or not? And that is how they do it. Now, FFT, what it does, it tries to do it. It tries to analyze a particular window of say whatever milliseconds, say 50 milliseconds, a window of 50 milliseconds. It tries to figure out if that is based on a spectrum, an energy spectrum signal. Now, if you use this particular, say if you have home inverters, how often do you even change them? You don't change them, right? You can go probably 10 years without changing them, and you won't detect one particular thing. But what happens is that over time, these systems age, and when these systems age, the frequency response of these systems, say if the Fourier transform of an arc versus what it should have been 10 years ago when it was a brand new system versus what it is, say, some years, 5 years down the line, 8 years down the line, it is not the same. And when this ages, we can't go figure out what is the new FFT band that I need to be figuring out, that is this right, is this wrong, is this an arc, is this not? We can't afford to do such things, right? So that's where this deep learning comes into picture, where we try to figure out. So this is just one picture. What you're seeing over here is of an arc. Say I'm trying to figure out of every arc window choice. Window choice can be anything. It can be 10, as small as 10 millisecond. It can be as long as 1 second and stuff. Now in this between, when you see this arcing start, you see that that is just the point where the arc happens. Now everything after that is still arcing. This is obviously a controlled setup, but you see that the signal afterwards is more or less similar to the original signal. However, it is not 100% same, correct? And that is what we need to detect. It looks as good as normal signal, but you need to detect that this is different, this is not 100% normal. So it should be there is something wrong. And that's where we figure out, we think of using deep learning. Now, so obviously deep learning requires a lot of data, right? It is not just I expect this to happen, so I guess this is fine and stuff like that. So for this to happen, what we usually do is that we have an arc setup. This arc setup is, it's a hazard that it needs to be done in a proper lab environment and stuff like that. We collect a lot of data. We collect data for, say, even something as 100-volt, 200-volt, a huge chunk of data. We do a lot of experiments, try getting a lot of data as to what is a normal condition, what is an equivalent arcing condition, and not just this, we not just playing around with the voltage. It can be different currents also. See, because ultimately, right, your home inverter, depends. If it's in the West, probably it's 100-volt or something. Here in India, it's around 220-volt is your home voltage supply. And same way, I think around the world, it's all of different voltages, as well as currents will be a lot more different. It's not one standard current that's there. And this is that we are just talking about home inverter space. It could be about photovoltaic grids, solar panels, EV batteries, everything. This infinite number of combinations. Now you can't really do all of these combinations. However, you can do a big set of this. You can take a sample population of these things and figure out, as well as, like, load variations is something that you need to take into picture. Say, for example, at your home, let's just take the case of home inverter. It is not just that is my home inverter. I'm just seeing that it's 100-volt. This is the current. That's not just enough. You also need to know, okay, for example, I switch on some heavy appliance, say a grinder or a washing machine or a microwave oven. Obviously, it pulls in suddenly more current. Now that is a different change in your thing, but it is not, it is not an arc. It is completely normal day-to-day stuff. You don't want that to be flagged as an arc. That's a false positive, right? Yeah. So these kind of things, all these kind of a lot of these sample population cases is what we try out, and based on that, there is we do neural networks. We try a few combination of neural networks. Now, what is this? See, after all, you can have a really large network to solve any kind of problem. That will definitely work. But here, what we are trying to do is to solve this in using a neural network that is also fittable onto a microcontroller. That's where the tinyML part of it comes in. It's not just any neural network, it's something that fits into a microcontroller. So whatever we've done, right? So 1 million max is the complexity of network that we are trying to achieve. Like, that's the high upper bound that I have. I'm just running it. Obviously, I'm at Texas Instruments. I will be using TI instruments. So TI C2000, this is one of these standard things that have been used for arc detection over the years, but for an FFT based algorithm. not deep learning based algorithm. Now, if I'm trying to do with the same to do an apple to apple comparison, I will be using the same device. Now I need to have the same accuracy, same kind of, better accuracy, but same kind of computational complexity and stuff. So 1 million max, that is just so small. Even mobile net is like multiple times bigger than this kind of model. Yeah, so we tried it on this kind of device based on all the data we have. We've not just, it worked great. It worked great. It gave much improved number of accuracy than the FFT based algorithm. Not just this, but also we tried the deep learning based on how we've designed the algorithm. We've noticed that it is not just that deep learning solves this problem. We are also trying to do tests that can I just train it on 100-volt data and see that if the same condition, the same model has learned enough for 500 volt or 600 volt or 800 volt. Surprisingly, for a lot of cases it does, because 100-volt data is a lot more noisy data. So one more addition here is that if you train it with a lot more noisier data, it generalizes so good that you don't need the sample population what you take. If you take it for a smaller volt but not more noisy data, it generalizes such well for even the larger set of data. Yeah, and all of this is fine, but one point anyone can ask is, why not just autoencoders? If we just used autoencoders, right? Autoencoders, you train what is normal, you say anything other than this is a fault. But the problem here again comes about load variations. If I have load variations, if I have different like this mixer grinder or oven, microwave oven kind of things, it'll cause a load variation that will still be flagged as a fault, and that's what you do not want. That's why you train a proper class. So ultimately, just concluding, yeah, so it is not just that our main point here was that amazing. So one, we've learned that you can solve this problem of arc detection with deep learning. Second thing that you're learning, it's not just any kind of network. That's something that needs to be fit on a microcontroller, which is always active, consuming very little power, still works. Additionally, if you have a hardware accelerator on your microcontroller, even better. It's going to be a lot more efficient in computing such things, and it's going to be very effective. Yeah, all of these are great. Now that you can extend these kind of things, I can solve arc fault detection, which is measuring current and voltage. For now, I'm just measuring only current. I'm just measuring current and able to solve this kind of a problem. Similarly, probably you can extend it more. Say vibration data is also 1D time series data. If I wanted to measure charge in a battery and predict the remaining useful lifetime, that's also 1D data. So ultimately, we are trying to also say that not just this, but you can solve a lot more problems using a similar set of ideology. Yeah, about that, thank you.
Great. Thank you, Adithya.